Welcome to section 6.2. In this section, we're actually going to go ahead and introduce what is called a definite integral and some background for that first. So last section, we talked about doing rectangular approximation methods, or RAM. Uh, RAM is a type of something of what's called a Riemann sum. And what a Riemann sum is that you're adding up areas. So it doesn't really matter what shape the area is that you're adding up. Uh, in RAM's case, we added up rectangles. So here we have right RAM, R RAM, and I can add up these integrals to estimate the area between the x-axis and the curve of t squared. And we talked about in the last section that this gets more accurate as n goes toward the number of rectangles n goes towards infinity. Well, the idea of a Riemann sum is I could do it with any shape. So we've done it with rectangles. We could do it with trapezoids, triangles, semi-parabolas, which are half parabolas. And those are actually all methods that we're going to be looking at over the course of the next couple of units here. But this idea of Riemann sum is adding up the areas, and then we need to do the limit of that sum as n goes to infinity. And that limit is called a definite integral. So it's the idea of doing a Riemann sum and then doing the limit as the number of shapes goes towards infinity. So this lovely notation here, I would be the definite integral, is the limit as the number of shapes goes towards infinity of the sum of, this is the height, and this would be the width. So if we were talking about rectangles, height times width is area of each rectangle, add those up, that's the Riemann sum, and then go towards an infinite number of those rectangles, makes this an indefinite integral. If this limit exists, we say the function is integrable, which is, well, just a fun word to say. So in terms of notation, this notation really is not very useful to us. It's not a big help. So if we wanted to talk about finding that definite integral on a closed domain from A to B, first off, the way we represent this part is we use a tall, skinny s. And this, whenever we see it, we just say integral. That's what this symbol is for. And it's a tall, skinny s because we are doing a sum. Then for the height of the rectangle, we just replace the c with x. Then for the delta xi, well, because we're going to infinity, that change in x is going to get really tiny, and so we actually get our differential dx. So here, if I see a c, I just replace it with x. My delta x just turns into the differential dx. But then what we have here is our domain is called the limits of integration. And it's telling us what x values we're actually looking between. So the first is the lower limit, which then makes sense because then the lower limit's going to go at the bottom of my s. Well, bottom and a little bit to the right, kind of like a subscript. Then b would be the upper limit, which will go up at the top, almost like a superscript for the s. So now this is the notation we use for definite integrals, and the way we would read this is the integral from a to b of f of x, and then you could say dx, you could say with respect to x, or you could just stop at when you say f of x. When you write it, you must include this differential. Must, that's not an option. When you say it, you don't have to say the differential. So for example, if I have here Limit as n goes to infinity of the sum from 1 to n of 3c squared minus 2c plus 5 delta x on the closed domain of negative 1 to 3. This is a definite integral. That's the definition of it. So this would be the integral. That's the limit as n goes to infinity of the sum of 3x squared minus 2x plus 5. Delta x becomes the differential, so this is with respect to x. And then negative 1 is my lower limit, 3 is my upper limit. If you want to, you can go ahead and try this next one. You can pause the video here and then restart it to see what the solution is. So this would be the integral from 4 to 8 of the natural log of x minus 3x dx, or with respect to x.